All right, good evening, everybody. Tonight we're going to be doing some past paper practice on momentum. So in the last lesson, I felt that we'd actually done quite a large amount of the momentum theory and that most of you were pretty good at it. So I thought what we'd do in this particular lesson is that we'd jump right in doing past papers. Now, in choosing the past papers, I realized there were two things that we'd overlooked just slightly. So I quickly want to recap both of those things before we go any further. All right, so the two things that I want to make sure that everybody understands and therefore that we've recapped are, I would like very much to go over the idea of elastic and inelastic collisions. The simple rule being that if a collision is elastic, then the kinetic energy is conserved. So if we have the kinetic energy being conserved, we can say, sorry, just give me 1 second. I've got to make all of these people go away now. There we go. Okay. We can say that the kinetic energy before the collision must be equal to the kinetic energy after the collision. And the only way to really do this is for you to work out the kinetic energy before and the kinetic energy afterwards. And it's, if you've got three objects, it's not just the kinetic energy of one object, it's the kinetic energy of all of the objects making up the system before the collision must equal the kinetic energy of all of the objects after the collision that make up the same system. So our rule is that if the kinetic energy is conserved, we can then say that the collision is perfectly elastic. But if they don't end up being the same, so if the kinetic energy before is not equal to the kinetic energy after the collision, then we'd say that the collision is inelastic. In reality, we only get inelastic collisions. In real life, if you have any sound made during a collision, you must have lost some energy. So therefore, you can't have a perfectly elastic collision. So elastic collisions are a hypothetical, wonderful thing that we can put in exam papers, but they don't really exist in real life. Also, if we deal with our elastic and inelastic collisions, I've seen a really nasty question, which I'm actually saving for Wednesday's masterclass, which involves a simultaneous equation where you are told briefly somewhere in the information that the collision is elastic. And that gives rise to kinetic energy before equaling the kinetic energy afterwards, which gives you one of your two simultaneous equations in a virtually impossible question. All right, it's a really, really nasty one. So that one I'm saving for Wednesday. But that's the only time they often ask you, is the collision elastic or inelastic? Can you work from it? Or they subtly just slip it in somewhere about being a perfectly elastic collision or inelastic, and you need to know or assume from there what they're talking about in terms of your kinetic energy. So that's the first bit about our elastic and inelastic collisions. The second thing that I just wanted to touch on is that quite often they overlap the section of momentum and they take it into your vertical projectile motion when an object strikes the ground and bounces back up. And the second place where they quite often bring things together is in our energy. Now, I have previously done lessons on work, energy, and power, so I'm pretty certain that all of you remember that potential energy is your energy due to the object's position above the Earth's gravitational field or in the Earth's gravitational field, and also the ability to fall. So your potential energy is equal to mgh, mass, acceleration due to gravity, which is your 9.8, times by the height above the surface, and that your kinetic energy is equal to 1/2 mv squared. Knowing this equation was also pretty important to what I just covered with kinetic energy being conserved. You also need to know that if we've got no external forces being applied, we can say that the mechanical energy is conserved, which means that the sum of the kinetic energy plus the potential energy at a certain position, I'm just going to call this initial, must be equal to the sum, maybe we could even put our brackets there, of the kinetic plus the potential energy, probably a better place to put them, final. All right, so we could put that as one of our rules. Now, these were the two things that I thought about that I had to just quickly touch on before we launch straight into past papers. All right, so what I've prepared with regards to your past papers for this evening's lessons is I've actually put together, I think there are 4 different past papers, and they're from old enough papers that many of you aren't likely to have done them, although I can't promise that your teachers wouldn't have turned them into worksheets. So maybe you have seen the pictures even if the numbers have changed. And what we're going to be doing is we're actually going to be running this a little bit more like the masterclass format, where I give you a question, you do it, and then we go over the answers. I think some of you don't get quite enough practice doing those, so I think it's a very good idea for us to make sure that you're used to how it works. All right, so I'm just quickly making these the right size, and then I'm going to share my screen. There we go. All right, so ladies and gentlemen, you should all, not that screen, you should all hopefully be able to see in a second the correct screen that I wanted to share. There we go. All right, sharing wrong screens. Okay, so our question here doesn't start with a number, and in fact starts with 4.3 because I took out the first half of the question because it wasn't relevant to what we're doing today. The question bits from where we start, so we could change our numbering here just to make it a little bit neater, 2 and 3. While traveling at 40 meters per second, the thief's car, okay, you missed the first half of the story. This is the thief's car. There was a thief, he was driving somewhere. And we have the thief's car of mass 1,000 kilograms collides head on with a truck of mass 5,000 kilograms moving at 20 meters per second. From the picture, you can see that they're traveling in opposite directions. After the collision, the car and the truck move together. That means they collide, they stick together, they move together as one object. You are asked to ignore the effects of friction. So the first question that I'm going to ask you to do, those of you who were here already on Tuesday, you'll know that we did a bit like this already. And in the master classes, we do the same thing, is I'm going to tell you which questions to do in one go, and then we'll pause and do other bits later. Okay, so I'm going to ask you just for now, if everybody can please do 4.1, state the law of conservation of linear momentum in words. There's a very good reason they say in words, and that's that if they didn't, you could write the formula and still get the marks. They quite often say in words to make sure you can't take shortcuts. Please, when it comes to these definitions, we're heading towards the end stages of your matric preparation. A lot of people assume that they know them. Oh, I know that definition, I'm not going to write it out each time. And the time when you discover that you know it but not well enough to write it out is in the exams, okay? In your prelims coming up, in your tests that are coming up, or in your actual exams. Please don't be lazy. From now till the end of exams, every time you get a past paper and it asks for a definition, write out the full definition. So I want you to do question 4.1. And then 4.2 is a calculation to calculate the velocity of the thief's car immediately after the collision. Please note, since the car and the truck move together, you're actually working out the velocity of the truck as well, but they've only asked for the thief's car, so you can interpret that how you wish. All right, you do not yet have to do question 4.3. We'll do that in just a second. All right, so I'm going to pause my screen while I work out the answer. Can I ask everybody else to please get started working on the question? Once you've answered both, I'm going to check who's done, and then when most of you are done, we're going to continue. All right, go for it. This is when we really get to practice. All right, I think I've nearly given you enough time. So I'm just quickly going to start glancing across at who's here. If you've already got an answer, please give me a thumbs up. Yeah, some of you guys are on the ball. You know what's coming next. Okay. Perfect. Just quickly going to give those of you who are taking a little bit longer a chance to quickly get it done. So we're not racing you too quickly. There's no point in me racing you to an answer. This is hopefully good revision for those prelims that are coming up just around the corner. All right. So I'm going to share at this point. So for question 4.1, the law of conservation of linear momentum, you had to have the words the total linear momentum of an isolated system remains constant, stays the same, does not change. All right. So the important words were that you had to have the idea that it was total and that it was linear. Obviously, it's got to be momentum, but they've kind of hinted linear momentum. And then conservation, they've already hinted to you should stay constant. Usually with this definition, it's an all or none. Then you had to calculate the velocity of the thief's car immediately after collision. Remember, you were told that after the collision, the two move together. That means they travel as one object. So the way that I do this is I say the sum of momentum before equals the sum of momentum afterwards. M1 VI1 plus M2 VI2 is M1 plus M2 times by VF. It is not the only way to write it out. There are other options. Sorry, there was a question saying, is conserved is fine here? So with the remains constant part of that statement, you can say anything that means does not change, stays the same, is constant, etc. All right. So over here, the important thing that you had to do was pick a direction as positive and stick with it. So we had 1,000 kilograms times by positive 40 because it's towards the right, plus 5,000 kilograms for the truck, times by negative 20, negative because it's going in the opposite direction, equals, the two of them stick together, so the total mass of their combined object is 1,000 from the car plus 5,000 from the truck, so 6,000 times by VF. I would recommend showing that as two steps, but if you've merged them, we're probably not going to penalize you too much for it if we can see exactly where you did it from. So here, when those two moved across, you ended up with negative 60,000 is equal to 6,000 VF. VF is negative 10 meters per second. In the question, it never said calculate the magnitude or the speed. It said calculate the velocity, which means it's a vector quantity and it needs a direction. So the velocity is 10 meters per second to the left. You could have said 10 meters per second in the opposite direction to its initial motion. You could have said anything where the direction clearly implied to the left or going that way. You could not, however, leave it as a negative and make the examiner interpret what it means. You had to decipher it for them. All right. The next part of the question said, research has shown that forces greater than 85,000 newtons during collisions may cause fatal injuries. Okay, please, that doesn't for a second mean that if it's less than 85,000, no damage, nobody can die, but it's usually kind of their cutoff that somebody looked up and found for you. The collision described above lasts for 0.5 seconds, so we've got our delta T. Determined by means of a calculation whether the collision above could result in a fatal injury. So I'm going to be very careful when I state my answer here. I'm not going to say it would or it wouldn't. I'm going to say it is likely or it is unlikely. Remember, people can die tripping over a stone. We're not going to go and say that you can't die because the force was too low. We're just going to say that according to this data, it's unlikely. All right, so whether it could result in a fatal collision, I would never say no. I'd say it probably wouldn't. Okay, there's just a quick question before we get started on that, saying in the calculation above, do we need to state which direction we choose as positive and negative, or will the examiner figure it out? The examiner will figure out that one of these is positive and one of these is negative. If you change it around, the basic rule is if that isn't negative, this one must be. If both are positive, it's wrong. If both are negative, it's wrong. I find to make sure that my examiner knows what's going on, and bear in mind they don't get your exam paper, I usually draw a little quick sketch with a positive somewhere on it, just that it's easier for them. You don't technically have to do it as long as you apply it. Okay, so I'm going to ask everybody using calculations to determine whether this force could result in a fatal injury. I'm going to pause sharing while I give you an opportunity to quickly do the calculations. Go for it. Is there a question, Seth? Please remember you could work out the force from either the truck or the car's perspective. It must be equal and opposite according to Newton's third law. So you can choose to work out the change in momentum of either of them. All right, if you have gotten to an answer, please give me a thumbs up so that I can see that you've gotten there. Okay, fantastic. Good, good, good. All right, I think we're just on half of you, so I'm going to give just a little bit longer. Got quite a bit of time today, and I don't want to race anybody. I'd rather give you a chance to finish your questions. All right. All right, ladies and gentlemen, I think most of you have got to the correct answer. So I'm going to show you my answer. My answer is down the left-hand side of my page. So you're just going to have to bear with me. I'm using the chalkboard bit of it. It's not really, it's just on gray. So what we had to do here was work out our force and see whether it was bigger than or smaller than 85,000. So you need to make sure that you use the correct formula. So F delta T is equal to delta P. Then what you had to do was say, well, our change in momentum is our mass, final velocity minus initial velocity over change in time. Please note either of those will get you your mark. Then you had to plug in. I did everything from the perspective of the thief's car. If you did it from the perspective of the truck, you should have got the same answers, but you'd have had different values. So I said 1,000 multiplied by, now my final velocity was -10. So I said -10 minus the positive 40 that we started off with over our time of 0,5, which gave me negative 100,000 newtons, which was 100,000 newtons left. If you had done it from the perspective of the truck, you could have done this with 5,000. Your final would be -10, but your initial here would be -20. Okay, so you'd have ended up with -10. How does this work now? Yes, -10 plus 20, which gave us 10 times by 5,000, which is 50,000, divided by a half, which gave us 100,000. And it would be positive because the force on this car is towards the left, the force on the truck is towards the right. Then we had to realize that our 100,000 newtons was bigger than the threshold value for injury, so a fatal collision is likely. Once again, not guaranteed, but likely. So it could result in a fatal collision. All right, now I went through quite a lot of that without actually checking how well people had done on it, mainly because I wanted to just get the whole lot together. So let's quickly see how many marks each of you would have got out of the total here, and the total is 13. So you had to get everything here correct in order to get your 2 marks. If you left off the word total, linear, momentum, isolated system, and the idea of constant, you lost your mark, any of those. For the second bit here, this was 6 marks. So 1 mark for either of these two. 1 mark. Over here, 1 mark for this side, 1 mark for this side. Okay, I'm going to struggle to give 6 marks here. Maybe we're going to have to do 1 there, 1 there, 1 there, 1 there, 1, 2, 3, 4, and then 5, 6. Okay, that's very generous, 6 marks. Please note if you wrote left, even if you wrote nothing else, you get a mark. Okay, over here, it's 1 mark for either of those. 1 mark for either what I've got in red or in black. Now, in red or in white. Over here, it was formula, substitution, comparison, answer. That yes, it is 1, 2, 3, 4. I think what they may even have done here is split this and given you a mark for the top and the bottom. It doesn't happen very often. So I'm actually going to be very cheating here. I'm giving you a mark for the 100,000. There isn't normally, but we're going to give you the mark and we're going to call it a substitution. So if you got a 100,000 and you used it or compared it here, then you get that mark. So that's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, and 2 there. All right. So, okay, so I've just got a quick question before we move across. And the question was, the person doesn't understand how you only had to work out the force of one object when they asked for the force of collision. Now, when we deal with Newton's third law says the force of body A on body B is equal but opposite to the force of body A back. So the truck will exert a force of 10,000 newtons on this car, and this car will exert a force of 100,000 newtons in the other direction. According to Newton's third law, body A on body B, the force of body A on body B is equal to the force of body B back on body A. You don't have to double the force or do anything strange like that. If you're asked here, technically it even gets a little bit more complicated because the forces on the car aren't exactly equal to the forces on the passengers inside the car. They may have had shock absorbers and all sorts of things, well, not shock absorbers, airbags in their crumple zones, etc. But we're assuming here that at a basic idea, that force was enough. So we never work out the force of both because they're going to be equal to each other. We also don't have to do anything strange where it's this one on this one and then we double them or anything silly like that. So as long as you can work out the change in momentum per unit time for one object, you can work out the force on both. All right, I hope that that makes sense. Okay, so I wanted to stop sharing at this point and go in and ask who got, so that was out of 13. Anyone here get 13 out of 13? Fantastic. All right, it's a good sign. I don't think this was a very difficult question, but this was used in a past exam paper. It's a realistic level of difficulty. All right, now just to make this quick, I want to ask who got above 10? So even if you put your thumb up for 13 out of 13, who got above 10 out of 13? Okay, above 10 out of 13 meant you overlooked something little, maybe a direction. Okay, that's a good sign. Okay, so 10 out of 13, you guys are in 67% or more, which is fantastic. Okay, obviously we want full marks for everything, but we're not going to get fussed if we don't get it perfect. All right, I'm now going to share my screen again, and we're going to move on to another question. All right. The second question, also from a past paper, is over here. Okay, I think you can all see it. So this question is one of the typical ones that we used to get. I haven't seen one for a little while, but they quite often do balls swinging down or a pendulum swinging down, hitting an object, the object moving, or bullets being fired from guns and into blocks, and the blocks then moving. So they start kind of incorporating multiple aspects to make it a little bit trickier. So I picked this example, and in fact, you'll see one of the subsequent examples I've got after this. Okay, that one's just somebody moving and grabbing somebody else. Then there's a cricket bat one. There should be one there. There's an example where we've got a bullet being fired into a block and the two moving off. So I don't know how far we'll get through all of these, but these are just to give you ideas of exam papers. Okay, and the kinds of questions and how they can link sections. All right, so question 4.
Excuse me, ma'am.
Yes?
What question paper is this?
I can't even tell you. I think most of these were from 2009, 2008 to 2010, that kind of range. I didn't write down which ones all of them were, but I decided that they were far enough back that you probably wouldn't have gotten to all of them necessarily. I know that most of the schools go back till 2015 in their exams, and I thought, you know what, let's give you things that you're not going to necessarily have done at school. All right. So that's part of the focus here, is that if I give you the exact one you've already done, it gets silly. So yeah, go and look there. There are not that many papers in that range. All right. So this question says, pleasure. A steel ball, there it is, of mass 0.5 kilograms is suspended from a string. Now you can assume that the string remains fully extended the entire distance. So this length, and this length are all the same. Sometimes they even get a bit sneaky and bring in angles, vectors, and things like that. Be ready for it. It is released from rest at point A. So if it's released from rest, we know that its initial velocity, we can even put in an I, is 0 meters per second, as shown in the sketch. As it passes through point B, which is 0.6 meters above the ground, the magnitude of its velocity is 3 meters per second. So we know here it's 3 meters per second. Please note they didn't give us the height at point A, so we actually can't work out the mechanical energy there. We can only do it from point B. So the magnitude of the velocity is there. Ignore the effects of friction. So we can assume that mechanical energy is conserved. All right. So question 4.1 says, write down the principle of the conservation of mechanical energy in words. So this is going back to the work that we did on the law of conservation of mechanical energy, but they often overlap the two. Sorry, I'm just going to quickly mute everybody. You can unmute if you've got a specific question, but otherwise it just keeps it quieter. So first question 4.1, write down the principle of conservation of mechanical energy in words. Once again, in words, so that you don't get away with just putting in an equation. And then secondly, calculate the mechanical energy of the steel ball at point B. So they're basically asking you, what is the mechanical energy of the steel ball at point B? Please note, I'm just giving you little hints here, you may not actually need to use this principle to answer this question, but you will use it at another point. Okay, so ladies and gentlemen, this isn't technically momentum that we're answering right now. We're starting off first of all with a little bit of work, energy, and power revision. But we may as well do it. Work, energy, and power was one of the first sections that we did, and that was nearly 8 weeks ago. So let's quickly do this. Okay, everybody go together. Four marks is way too generous for this. All right, if you're done with that all, please give me a thumbs up. Good. Good, good. I'm interested to see who's overthought the first question and not answered it and answered a different question. Make sure that you answer the question that's being asked. All right, I'm going to start sharing now. I think that should be enough time unless you've gone down the wrong tangent, in which case it's a little bit of a lost cause. So let's have a look. Question 4.1 said, write down the principle of conservation of mechanical energy. You had to have total mechanical energy of an isolated system is conserved. Okay, total mechanical energy, isolated system, and conserved in order to get 2 marks. I'm not going to decide how we split up the marks for definitions. It's safer to just say all or none, and then you're sure that you're going to get the marks if you're going to get them. For question 4.2, you didn't need to go from B to C, you just had to stay at B. So when we were asked to calculate the mechanical energy, it was mechanical energy is the sum of the potential and the kinetic energy. Your potential energy is mgh, your kinetic energy is a half mv squared, mass is a half, g is 9.8, the height above the surface is 0.6, plus a half, m is 0.5, v is going to be our 3, which we square, and I got an answer, I hope it's right, of 5,19 joules. So I'm going to ask just quickly, who got the same answer? You got 5,19 joules? Okay, good, that's a good sign. Okay, anybody who didn't, it may be that you weren't quite as fresh on your mechanical energy as you hopefully will be before you write your prelims. So please, if this has suddenly been something that's been a bit of a surprise, make sure that you go back and you revise that. There is a full set of videos that I've done on work, energy, and power, so you can go in and have a look at that. Okay, so there's a question here regarding the marks. Technically, if you've written this or this, you get the formula mark. I get a bit irritated with it because I believe that you can't actually do the substitution without writing this line. But my experience in marking is that they give you for either of those two, they don't get too fussy. This being for 4 marks, there's probably 1 mark for that side, 1 mark for that side, and 1 mark for the answer. You've got to have joules or you lose your answer mark. Okay. Then the question says, as the steel ball swings through its lowest position, which means that here the height is 0 meters, at point C, it collides with a stationary crate, so the velocity is 0 meters per second, of mass 0.1 kilograms. I don't know if all of you do this drawing all over your picture as you get to it, but it's a very good way to make sure that you don't miss anything. Immediately after the collision, the crate moves at a speed of 3.5 meters per second to the right. So the crate moves to the right. There's nothing here that says that the crate and the ball stick together. So the ball afterwards can either carry on moving that way or it can move back. So our question here asks us to calculate the velocity of the steel ball immediately after the collision. Now you're going to have to use 4.1's law of conservation of mechanical energy to work out the velocity of the steel ball when it hits the block in order to be able to use law of conservation of linear momentum to work out the velocity of the steel ball immediately after collision. Now, I want to just quickly ask at this point, who feels confident that they can answer this question? It's not a very difficult one, but it's got many parts. Whoa, I haven't had a single thumbs up. Who feels confident? Yay, 5 of you. Okay, it's a little bit more than that. Fantastic. So what we're going to do is I'm going to encourage you to start solving it. I'm probably not going to give you enough time to get to the full solution because I'd like to work through this with anybody who's struggling. So those of you who are confident and who know you're going to get it, please go ahead of me. I'm going to give everybody just a little bit of time to ponder how they'd start on their own, because I think it's very important to get used to and to overcome that initial fear of where to start. Okay, so start thinking about where you'd start. Draw a picture if you need to, work from there. Okay. All right. Can I have a quick show of hands? Who's waiting for me to tell them where to start? Oh, that's good. That's good. That's a good sign. Yay. Well done. Okay, one person's waiting. All right. So, ladies and gentlemen, I'm going to hint to you where to start. I started this one by drawing a picture of how I see it. Please, if you've already started and you're on your way, ignore me and keep going. I started with a picture that said the ball C comes in here. It's got 0.5 kilograms and I don't know how fast it's going. I know that I've got a box with a velocity of 0. This is my universal symbol of it collides. There's a boom. Afterwards, the box goes to the right at 3.5 meters per second, and I don't know if this ball goes to the right or to the left. So my first bit of advice to you is to use the law of conservation of mechanical energy, which you worked out that the mechanical energy here was 5,19 joules, and use that to work out the velocity of the ball C at the bottom. So that is your first bit of where you need to start. That is your first hint. Try and work out the velocity of the ball when it reaches point C. Go for it. All right, I'm going to quickly check in. Who's got the velocity of the ball at point C? Okay, good. Good, good, good. All right, let's just quickly check in again. Obviously, if you've still got all the answers, and that's wonderful. So I'm going to quickly share my screen again. What I did here was I said, and please do this, don't skip steps here because you may lose marks. I said the mechanical energy of C equals the mechanical energy of B. I forcibly implied that I knew that I was doing the conservation of mechanical energy. So my 5,19 is equal to mgh plus a half mv squared. I then subbed everything in, even the zero height. I know it's a pain, but you don't want to risk losing a mark if you've got a sticky examiner. From there, I took my 5,19, divided it by a half, divided by a half. That gave me v squared, square root both sides, and I got 4,556 or 4,56. Can I ask at this point who got the same answer? 4,56. Fantastic. Now what you're going to do from there is that your initial velocity here is 4,56 meters per second. If you wish you could stick with 4,556, that's fine. So you've got the initial velocity of the two, you've got the collision, and you've got the final velocity and mass of the second, but you're missing information here. So you're going to start with sum of momentum before is equal to the sum of momentum afterwards. Oh, I don't know what letter that is. I don't know what letter that is either. Sum of momentum afterwards. And what you're going to do from there is you're going to solve for the velocity. All right, I'm going to pause here again because I think many of you at this point hopefully have an idea as to how to progress from there. All right, go for it quickly. Remember to pick a direction as positive and to stick with it. I can't tell you yet. I haven't got to the end of my answer. I'll let you know as soon as I get there, promise. Ooh, I got a very big value. That doesn't make sense. Let me try again. Okay, I've got a bit of a better answer. Okay, I got the same answer as you. That's a good thing. All right, just quickly, in reply to the question, do you need to include the second line of the equation, which was the mgh plus a half mv squared? I would say yes, I usually do. But once again, I think it's more because that's what I plug into my equation. That's where I do my substitution. All right, who has got to their final answer? Who got an answer of 3.86? Fantastic. 3.86 is what I got, so I think we're going to assume it's the right answer. All right. So I've stopped sharing there. So what I did, and I know I'm writing different colors on different colors, I hope you can still see, is that with all of the sums, I said sum of momentum before is sum of momentum afterwards. M1 VI1 plus M2 VI2 is M1 VF1 plus M2 VF2. 0.5 times by the value I got over here. Please, if this was wrong, as long as you used it in this equation, you would get marks for this substitution. 0.1 times 0. Once again, I would caution you against ever leaving off a 0 for substitution. Even if we're smart, we can't say that the law of conservation of momentum says that the momentum of the one is the momentum of the other two. We got to put in that this one's 0, rearrange, and then work through. Now, this was for 7 marks. My understanding of where the marks are there's 1 mark for either of those 2 equations, 1 mark for that side, 1 mark for that side. You also had to do all of this. So there's 1 mark here for using that bit. I don't know if you'd get, I think there's probably 1 mark for conservation of mechanical energy, but be careful. If you just started with this value and you weren't clear that you weren't using the value from B, you were saying B equaled C, etc., you might lose that mark. So there's 1, 2, 3, 4, 5, 6, 7. Once again, if you've just got the direction of right, even if nothing else is correct, you would get the mark there. All right. So showing that if you got the correct definition here, you got 2. We've got a total here, once again, of 13 marks. Please, I think these are rather outdated totals. I'd like to ask just quickly if everyone can quickly take all the screenshots they need. I want to just quickly check how everybody did on that one. All right. Can I have a quick show of hands? Who got full marks? Full marks? Fantastic. All right. Next question that's probably more important. Who got full marks on this one but didn't get full marks on the previous one? Yay, okay. Now that's what I actually want to see because that says that you've improved. All right, well done to everybody there. We've got another 12 minutes left. I think I'm good to do one more if everybody else is still good to do one more. Is that okay? All right, fantastic. So we're going to go back in. Now I've actually set up a couple of questions here, so I've not got to make that awful decision about which one we're going to do. But I'm going to have a look just quickly and see which one's likely to cause you issues. This one here, I'm just quickly going to run through them. There's a man on roller skates, and he sees a boy in front of him. He grabs the boy, picks him up, and they move together. This one's got a question on elastic collisions, which is rather nice. So I may do that one. This one is very similar to what we did in the last lesson with impulse, although it does do ratios of heights. And this collision one, I think I'm actually going to do the third one because I think that one is very similar to the one we've just done. All right, so we're going to stick to the three in order that I put them in. All right, I will, if you wish, send this on to the WhatsApp group and you can go and have fun practicing it on your own, the other ones we didn't get to. So I'm going to ask everybody right now, we're going to do, let's do the first question. I'm going to do just one at a time and we're going to go through them almost as fast as we can. So I'm going to pause sharing. I'm going to ask everybody to try and do it. This one should be using the conservation of linear momentum. Go for it. All right, ladies and gentlemen, who's got an answer? Okay, good. Good, good. If you got an answer, I got an answer of 3 meters per second, just over 3. So technically 3,01. Does that sound right to most of you? Okay, good. All right, so I'm going to stop sharing. And I'm going to show you what I did. So the first thing that I did that may surprise you is I drew a picture. I find that I get totally confused about what I'm doing if I don't have a picture. So there's the man, there's the boy, there's his roller skates, there they collide, here he picks him up. Together they've got a mass of 109. That told me that we have 2 separate objects becoming one object. Please, you don't have to use the exact same formulas as I've got here. Either of those 2, I should do a different color, either of those 2 will get you a mark, okay? This is a 3 mark, so sum of momentum before is sum of momentum afterwards. All that formula gets you a mark. That substitution gets you a mark. This substitution gets you a mark, even if it's slightly different. So if you had M1 times by 2.4 and M2 times by 2.4, that's perfect. I then went and worked it out, disappeared my 0, got an answer of 3,01 meters per second. Now, there was a reason that I didn't say to the right, even though I technically did have a positive direction and stick with it. The question asked about the man's speed. Speed is a scalar quantity, therefore it doesn't require a direction, so you were fine. All right. Can I quickly ask who got the same answer? Same method? Fantastic. Okay, well done. Next question. Is the collision elastic? Use a calculation to support your answer. Now, the first thing is they've asked you a question. Your answer must start with yes or no. I've noticed in the marking recently that they're starting to get fussier, but if you didn't answer the question, they don't mark anything else. feels a little bit unfair for them to penalize you for a full 6 marks if you didn't say yes or no, but did all the calculations. So maybe they wouldn't do it, but they have started doing it recently in chemistry. So you want to be very sure that you actually answer the question properly and you don't get penalized for not having that bit. All right, please, can I suggest right now that everybody does this? Oh, if you put in a direction when you're not asked for a direction, they usually just ignore it. But I find that if I do feel really inclined to put in a direction, I would go and put it in brackets so that they know that I knew I didn't need it. Okay. Otherwise, it becomes a little bit iffy as to whether they have to give you the marks. Okay. Don't tempt fate. All right. Can everybody please do question 6.2? All right. Is everybody nearly done? Everybody nearly done? Okay, fantastic. So what I did here, and you didn't have to do it exactly the same way that I did it, is I said the kinetic energy is a half mv squared plus a half mv squared. I know this boy isn't moving, but you still got to show a half times mass times 0 just to be safe. So I put that in anyway. It's one of those things where it's painful because you know that it's going to be 0, but I recommend you do it rather than leaving it off. And I got 394.11 joules. Afterwards, I said, well, they're one object, so I just did a half total mass v squared. You're allowed to do that as long as you got one object, and I got 313.92. So you can see that we've lost quite a large number of energy, a large amount of energy. You could even have done the difference between the two and said so many joules of kinetic energy is lost, but here I just said, no, the collision is not elastic. I probably should have said 394.11 is not equal to 313.92, or something about the fact that the change in kinetic energy is not 0, or the kinetic energy before is not equal to the kinetic energy afterwards. So then, therefore, the collision is not elastic or inelastic. Very important that you answer the question, is the collision elastic, with a no. All right. We've got 2 minutes left. Before I do that, I just quickly want to check who got that correct. You got that answer correct with all the calculations as well? Okay, fantastic. Hopefully, if you didn't, even just watching this, next time when you have to do it for marks, you'll get it correct. The last question here says, after grabbing the boy, which is this scenario over here, they both continue at 2.4 meters per second along a straight line until they arrive at a loose gravel surface near the end of the path. They now move at a constant acceleration in a straight line through the loose gravel for 2 meters before coming to rest, and you're asked to calculate the magnitude of the force exerted by the gravel on the surface, gravel surface on the man and the boy. Now, most of you at this point probably have your brain set in momentum. So you're going momentum, so you're going to try and do F delta T is change in momentum. Now, while you can do that, it's going to involve a lot of extra work because we were never given the time. And although we do know that they start at 2.4 meters per second and they finish at a different value, I'm going to tell you that it makes a lot more sense here to work out force from my perspective by instead saying F net is equal to MA. I know it's the same equation. We did discuss it in the last lesson, but doing equations of motion. Doing equations of motion where we have VI, VF, A, delta T, delta X. So we say, well, our initial velocity is 2.4 meters per second. Our final velocity is 0 meters per second. We're looking for the acceleration and we get that he covers 2 meters. The equation without delta T, I'm just going to have to pick a color that shows up nicely here, is VF squared is VI squared plus 2A delta X. You'd use that, calculate A, take A and mass, and work out F net. So that is how I would approach the last question. I just mentioned this one to you because I think a large number of you would be so set on having to use the impulse formula that you tried to use this formula, but you'd find you fall very far short with the time. The easiest way to get rid of the issue that you don't have the time is to work out acceleration using equations of motion, which is another way. All right. Can I quickly just ask by show of hands, because I know we're going over time, who would like me to quickly finish this last one with you? Okay, cool. I'd rather finish it with those of you that then want to. If you need to leave, please don't worry, you're welcome to go. So here we're going to have 0 squared is equal to 2.4 squared plus 2 times A times 2. Okay, I'm doing this one with you, not waiting for you with you. So I'm going to get an answer here, if this moves across to the other side, of negative 5.76. And that is going to equal 2 times 2 is 4A. So if I divide this by 4, I get that the acceleration is negative 1.44 meters per second squared. Negative because it's decelerating. Negative will also tell us the direction of the force, but since they've said magnitude, we don't really care. So here we're now going to jump in and say, well, F net is equal to MA. My mass of the man and the boy, because it's the force on the man and the boy, means we're going to deal with the mass of both, which is 109 times by negative 1.44. Please, that is a very badly drawn 0. If I then times this by 109, I get that the force is negative 156.96 newtons, and you can change the negative to be 159.96 newtons, and this would be in the opposite direction. Remember, I was the person that drew the picture going this way. They never actually told me that. So if I've drawn a picture, I could probably say to the right because it corresponds with what I've done, but it's a little bit of a risky move putting in a direction that they never told you about. All right. I hope that that makes sense to everybody. Please just quickly take a screenshot of it if you need it. Okay, because I'm going to stop sharing. All right, I hope that that made good sense to everybody. Please go on to Siavula and go and practice this section. I'm very keen to do a rather challenging masterclass on this with nasty questions. All right, have a lovely evening, everybody.